What's going on, guys? Welcome back to another video. And in today's video, we'll be coding a binary search in Python. Before we dive into the code, let's first talk about what a binary search is. So a binary search is an efficient searching algorithm that determines if a value is in a sorted array. And it does this by repeatedly dividing the array until the element is either found or the list is empty. So let's take a look. So traditionally, if we wanted to find an element in a list, what we do is we simply traverse the list, right? We go through each element in the list and say, hey, is this element the element we're looking for, right? So if I have a list of, say, 5 items, and I wanted to find 4, what I would do is I would go through each element in the list all the way until I get up to 4, and I'll say, hey, 4 is in the list, so I'll return true, right? This is what we call a linear search, because we're searching the list one by one until we find the element we're looking for. Now, the reason why this is problematic is because if this list is like really big, like we're talking about billions, this element that we're looking for, theoretically, it could be the last element in the list, and that would take a really long time. So this is where binary search comes into play. And like I mentioned earlier, it works by repeatedly dividing a sorted list or array in half until it finds the element we're looking for. So let's say I have this exact same list with the exact same numbers, right? Except this time it's sorted. So I'm gonna have 5 elements. I'm just gonna quickly sort this. So it's sorted from smallest to largest, right? And now say we're looking for 9. So 9 is the last element in the list. Now, what we do is we start in the middle. So we split the list in half. So we start here at 5. And we compare the number we're looking for. So we're looking for 9. We compare that number to the middle number, which is 5. 9 is bigger than 5. And we know the list is sorted. So we know that 5 and all the elements to the left of 5 can be crossed out, because it's impossible for 9 to be on the left side of 5, because 9 is greater than 5. So now we're going to examine these 2 elements. And depending on how we write our algorithm, actually the way I wrote it, it would look at 9 next. And it would say, hey, 9 is in the list, and boom, it's here. And this is a binary search. All right. So this took 2 steps, even though 9 is in the back of the list. The first linear search took 5 steps. So a binary search is much more efficient when it comes to larger data sets. And we'll talk about time complexity in a later video. But binary searches, when it comes to larger data sets, is proven to be faster than a linear search when it comes to program speed and memory. Now let's actually code it. So here I have a list of steps that we would take to implement this binary search algorithm. Now, when implementing a binary search, the first thing we always have to do is sort the list, because that's the basis for how a binary search works, right? So we're going to sort the list, then we're going to get the middle index of the list. So we're just going to divide the length of the list in half. Next, we're going to write this algorithm recursively, so we have to define a base case. And in this case, the base case is the length of the list being greater than 0. So if the length of the list is greater than 0, we're going to do these next 3 steps. So the first one is, if the number is at the middle index, we're going to return true. So that's really how a binary search works. We're going to divide it in half. If the number is at the middle index, we're going to return true. If the number is greater than the middle index, so if the number is on the right side of the list, we're going to return the binary search algorithm, except we're going to start the list 1 to the right of the middle index, so middle index plus 1. Conversely, if the number is less than the middle index, so it's on the left side of the list, we're going to return binary search, except we're going to slice the list from the beginning of the list all the way up into the middle index, excluding the middle index, right? And lastly, if we reach our base case and we haven't found the number, we're just going to return false because the number is not in the list. All right, now let's code it. So first thing I'm going to do here is I'm going to define a function called binary search. It's going to take in a list and the number we're looking for. All right, now I'm just going to follow these steps. So one by one, I'm going to sort the list. So let's do sorted list equals, and we're going to use the inbuilt sorted function that Python has. All this does is it returns a list sorted from smallest to largest. So sorted list is now sorted. And next we're going to get the middle index of the list. So I'm going to create a variable called mid. And it's going to be equal to the length of, let's do sorted list. And we're going to do integer division. So integer division is 2 slashes. The reason we're not doing regular division is because imagine the length of the list is 5. If we did regular division, it would return a float, which is 2.5. So 5 divided by 2 would be 2.5. That's not a valid index. So we want our middle index to be an integer. And integer division will round down. So 5 divided by 2 would be 2. All right. Now we're going to define the base case. So the length of the list is greater than 0 is our base case. So if length of sorted list, or actually let's do list because it's the parameter. If length of list is greater than 0, we're going to do these next 3 steps, right? So if num is at middle index, if sorted list num, so if the middle index of sorted list, mid, is equal to num, then that means, well, we found the element in the list. So we're going to return true. All right. Now we're going to do an else if here. Else if, I said num is greater than middle index. So num is greater than sorted list mid. We're going to return binary search with the list starting at middle index plus 1. So we're going to slice the list. So we're going to input as an argument sorted list, and we're going to start with middle index, so mid plus 1, and we're going to end at the end of the list. So we can just leave that empty. That's how slicing works. And we're always going to put num as our argument because we're always going to be looking for this one number. In else, if number is less than the middle index, so number is on the left side of the list, we're going to return binary search. And it's going to be the complete opposite, right? We're going to start from the beginning. We're going to go up to mid. Now we're going up to mid here because mid is exclusive. So it's really going up to mid minus 1. And again, we're going to input num as an argument. So that satisfies our base case conditions. Let's do the last point here, which is if we reach our base case and we haven't found the element, we're just going to return false. So let's go through this one more time. We start by sorting the list. We get the middle index of the list by dividing the length of the list by 2. We're going to define our base case if the length of the list is greater than 0. If the middle index is equal to none, return true. If the number is greater than the middle index, return. So we're going to return from the middle index plus 1 to the end of the list. If the number is less than the middle index, we're going to return from the beginning of the list all the way up to the middle index, right? And again, if we reach our base case, we haven't found the number, we're going to return false. Now let's test it. So I'm actually going to use the exact same list that I created here on paper. So let's do new list equals what I have, 8, 1, 5, 9, 4. Now let's print binary search new list, and let's look for the last element 4. This should return true. It does. Let's look for 8. This should return true. Now let's look for 3, and this should return false. It does. All right, so it seems to be working just fine. Again, this is much more efficient than our linear search. Like I said, imagine if the list was the length of 1 billion and the element was at the end of the list. So that would take 1 billion steps. Here, all we're doing is we're dividing the list of the length of the list in half. So it immensely speeds up the searching process. That will conclude this video. If you enjoyed it, make sure to like, comment, and subscribe. And I hope to see you in the next one. Take it easy.